Good morning and welcome to the very first YouTube Live virtual lesson for AP Calculus BC. Today is Wednesday, March 25th, and AP Calculus has the distinct honor of kicking off the College Board's live lessons and AP review sessions that will be airing daily Monday through Friday right here on YouTube. My name is Brian Passwater, and I'm an AP Calculus teacher at the world famous Speedway High School in Speedway, Indiana, home of the Spark Plugs. And I have the privilege of teaching some of the most amazing and wonderfully talented and dedicated students that I've ever worked with. And I am beyond excited to work with each of you that are listening right now and following along. I'm joined today by my good friend and fellow AP Calculus teacher, Tony Record.
Hello, everyone. As Brian said, my name is Tony Record, and I'm a calculus teacher at Avon High School in Avon, Indiana. And we want you all to know that we're truly blessed and honored to be able to work with you over these next few weeks. And together, we have the best possible chance of being successful on your AP exam in May.
Absolutely. So before we jump into today's lesson, because it's our first session together, I want to go ahead and share a little bit of information with you to let you know what you can expect over these next 5.5 to 6 weeks, not only in this course, but probably in all your other AP courses that you'll be watching live daily lessons with. Every morning at 9 a.m. Eastern time, Tony or myself, we will be here with you to teach you, review with you, and most importantly, help you prepare for the AP Calculus BC exam coming this spring. For the next 2.5 weeks, we will be covering specific topics that are in the AP curriculum. And every one of those topics for 13 days will include daily lessons that are going to focus on 3 really important things. Number 1, we're going to make sure that we teach you the topics and the concepts that are in the curriculum. Number 2, we're going to make sure that we connect those topics and connect those concepts to the previous things that you've learned throughout the year. And then finally, number 3, we're going to make sure that we connect all of these topics to the actual AP exam so you can see not just the content and the concepts, but how they're going to appear or help you get ready for the AP exam. With all of the extenuating circumstances that are affecting all of us right now across the country and across the world, the College Board has announced recently that the 2020 exam administration this spring will have some select topics that will be not included on the actual AP Calculus exam. Tony and I will be very diligent about indicating this during our lessons. However, even though we're covering some topics that are not tested on this year's exam, those topics are still highly important, and we do encourage you to engage and learn all those topics if possible in order to be best prepared for future coursework beyond the AP exam. We're very aware of the AP exams, and we're very aware that they're coming up around the corner in a few short weeks. And so every single lesson that we cover over the next 6 weeks, whether that topic is being tested or not, will be designed to help you prepare for this year's exam as well. So even the non-tested topics will include many strategies that are connected to the AP exam, and a lot of the previous content will be intertwined and reviewed along the way. So that way, every single session that you attend on here will get you closer to success on the AP exam. Following that initial 2.5 weeks that we're starting today, where we cover selected topics each day from units 9 and 10, we're going to start to transition into a full 3 weeks of AP exam review and prep. Tony and I are both extremely ecstatic to be working with you each day, and we hope that you find each of these sessions to be helpful, enjoyable, and beneficial to you. One last comment I want to share before we jump into our lesson today. If you look down in the comments of the YouTube channel under this video, you should see a link that has a link to some resources. This link will connect you to all the resources that Tony and I will be using over these next 6 weeks during our sessions. Feel free to click on that link. It'll be the same link for every video. It's one link, and in there you will see the materials that we're doing, and then following each session, you will see answer keys typed up for the sessions that we cover. So feel free to download those materials or print them out. That way you're able to follow along, take notes, and practice with us for the AP exam. So let's go ahead and get started, shall we? So every single one of these sessions will start with a short warm-up, and the warm-up will be something that we typically covered in the previous lesson that gets you ready for the upcoming lesson. But since this is our first lesson, let's start with this. So today's warm-up says for any time t greater than 0, we have a particle p moving along the x-axis with position x of t. and x of 0 is 0. The velocity of particle p can be modeled by v of t, and it's given in the graph above. And during the same interval, we have another particle, a second particle q, that's moving along the y-axis with position y of t, and it's known that y prime is less than 0 for all t greater than or equal to 0. And there's some selected values for y of t given in the table above. So the question is, for our warm-up, at time t equals 8, determine if particles p and q independently are moving toward or away from the origin. So in this warm-up already, we can see a lot of things going on. This is a really good example of what you might see on the AP exam in terms of connecting representations, connecting different functions, and connecting ideas. This is a question that's from earlier in the year that would be typically an AB course, but also included on the BC exam. So what we like to do on these warm-ups is give you a few minutes to think through them, process them, and see if you can sketch out or start to solve some of the problem. So I'm going to go ahead and turn this timer on and give you about 2 minutes, if you have a chance, and either see if you can figure out the problem, work it out, or if you're not 100% sure, spend the next minute and a half trying to think through what the important information would be and how you might start to tackle a question like this that has so much information and so much stuff going on. So I'll give you about a minute and a half, and we'll work through it together. So before we jump into working this problem out together, I want to point out a couple of things. I think as you start preparing for the AP exam and getting closer and closer and closer, one of the things that you will notice, if you haven't already, is that the AP exams do a really good job of testing your conceptual understanding. You'll probably hear me and Tony use that phrase quite a bit in the next 6 weeks, because the College Board and universities and colleges around the country want to know more than if you can just compute or solve a couple of problems. They want to see if you truly understand the ideas, the concepts, and the underlying theories that are going on in the topics that you're learning. And so you see these questions that do a lot of connections. And at first they seem daunting if you haven't done many problems like this, or if it's been a while since you've had a chance to do these problems. And so I really want to encourage you, when we have a chance to do a warm-up or an AP practice problem at the end of today's lesson, or even the examples that we do throughout the lesson, really try on your own as we're doing them and giving you time to start them, to try to see if you can have a way to either solve them or start them out. Because what you learn how to sort of break down the problem, figure out what's important, and get some of the strategies that Tony and I will share with you these next 6 weeks, I think you're going to find yourself getting better and better each day, and getting better and better at solving problems that maybe in the beginning of these sessions you wouldn't feel as comfortable doing. So we're going to go ahead and kind of break this problem down together. And so what I'm going to do is highlight a couple of pieces of information, which I think is a really good strategy. So when you're working through these problems, start realizing that we have a couple different things that are going on. Number one, we have this idea that we have two different particles, right? So we have particle P, and I'm going to underline that. And particle P is moving along the x-axis. So I like to imagine we've got, an x-axis here, and particle P is moving along this axis back and forth somewhere. And this would be for particle P. But then we also have the second particle Q that kind of gets introduced later on, and it's not moving along the x-axis, it's moving along the y-axis. And so I'm going to put this particle Q in red. And so now I have sort of this y-axis go up and down, and this is going to be how particle Q is moving. So this is particle Q, and then the horizontal x-axis is going to be particle. And so we have these different particles moving along different axes. You'll notice I put them separately because in calculus AB, we kind of treat particle motion only on one direction, one axis. But today what we're going to look at is how we combine these two things into one coordinate system through the idea of parametrics. So what do we know? Well, I'm going to start with particle Q because I think it's going to be a little bit easier to solve. We know a couple of things. We know the position is given in this table. So we have a table of values, and in that table, these are position values for particle Q, right? And we want to know at time 8 specifically whether the particle is moving toward or away from the origin. Well, what are we going to have to know to answer that? Sometimes students think, well, if I want to know if it's moving toward or away from the origin, I only have to know which direction it's moving. Is it moving left or right? Is it moving up or down? Is the velocity positive or negative? The problem with that is you can be moving up away from the origin or up toward the origin. We have to know more than just which direction you're going. We have to know where you are as well. We have to know where you are plus which direction you're going. And those two things combined will allow us to know whether you're moving toward the origin or away from it. So for particle Y at time 8, which is given in the problem, we can see in the table, we have this value right here at time 8. And we actually know that at time 8, particle Q is at -4. This is the position. So we know that the position is at -4 at time 8. And we know from the original problem that y prime is less than 0. If we think about these connections, we know that y of t represents the position of the particle. And then with particle motion, if we take the derivative of y, or the position, that ends up giving us the velocity. And if we take the derivative a second time of position, that will give us the acceleration. So if y prime is less than 0, this means that the velocity of particle Q is less than 0. And since particle Q is moving up and down the y-axis, a negative velocity indicates that particle Q is moving downward. Well, we see the origin right here. So we're starting at -4 and moving downward because we have a negative velocity. This is going to indicate to us that particle Q is moving away from the origin. Now let's go back to particle P. It's a little bit different because we know particle P, we don't have the position at time 8, but we do have a velocity graph for particle P. So now we get to connect another idea from earlier in the year. So hopefully you're already starting to see how, even though if we cover a topic that may not be tested on the exam, we're going to be making a lot of connections because all of those previous topics that you've learned that are going to be tested on this year's exam are really embedded. And those are the things that drive and help us to build on these new topics. And so each one of these lessons that Tony and I are going to cover are going to be really rich with built-in review, exam prep, and getting you ready for what you're going to experience this year, but as well as beyond this course. And so I need to figure out what the position of particle X is at time 8. Well, if you might remember, we have this ability to create any accumulation function using the fundamental theorem of calculus, that if I want to know the X position at time 8, we're going to have to use an initial position that we were given, which, by the way, we knew that X of 0 is 0. So X of 8 is going to be X of 0 plus the integral from 0 to 8 of v of x. And we know that X of 0 is 0. So now in order to sort of finish out this problem, we just have to figure out the integral from 0 to 8 of the velocity. Well, luckily they gave us a nice velocity graph, and we know that the definite integral from 0 to 8 is just the signed area between the velocity graph and the x-axis from 0 to 8. And so as we kind of build this up, we get this little region right there. So the integral from 0 to 8 of the velocity is going to be the signed areas of those three shapes. Thankfully for us, all of these functions are linear, so we can figure out the area of those using some basic geometry ideas. So I'm going to do that right here, below here, to have a little bit more space. And we have the integral from 0 to 8 of the velocity of particle p dt. And you can break up these areas however you want. Some of you might recognize this first little region right here is a trapezoid. Some of you might be more comfortable thinking about this as a or a square and a little triangle. Either way is going to be fine. I'm going to do it as a trapezoid because it allows me, number one, to get some practice using some trapezoidal approximations. And number two, I can do this area in one formula instead of breaking it up into two, which means fewer calculations, fewer numbers, fewer chances for mistakes. So this first area here is a trapezoid, and our area of trapezoid is 1/2 the height of the trapezoid, which we can see in this case is 1, times the quantity of the sum of the two bases, and our bases are going to be the parallel sides, so that'd be 1 plus 2. And then I get to the second region here, and we see it's a triangle, and the base of the triangle goes from 2 to 6, and the height is 2, but notice this triangle is beneath the x-axis. So there's a bit of misconception that happens a lot. When we say the word area, area is always a positive value. Area is positive by definition, because we're talking about a geometric shape and how much space something can hold. However, when we're doing definite integrals, especially with graphical representations, we typically call this the signed area, meaning since this part of the shape is below the x-axis, we're going to give it a negative value when we compute it. We're not saying the area of the triangle is negative. We're saying that the definite integral for that portion is negative because we're basically losing accumulation there. So we're going to do a little minus here because it's below the x-axis. And a triangle, the formula is going to be 1/2 base times height. So it's going to be 1/2 4 times 2. And then finally, for our last portion here, we have another trapezoid that's identical to the first one. And so we know the area of that is going to be 1/2 1 times the quantity 1 plus 2. Now, a little bit of arithmetic here. I'm going to save you some of the details, but if we were to compute all these, we would end up with -1 for our integral, which means that x's position at time 8 is going to be 0 minus 1. Remember, the 0 came from our initial position given to us in the problem. That won't always be 0, but in this case it was. And so x of 8, looks like a 3 there, I'll make it to an 8, is equal to -1. And so in my x graph, we know that particle P is starting here at -1. And now I have to figure out which way it's moving so I can determine whether it's moving toward the origin or away. Well, again, we're looking at 8, so I want to figure out what is the velocity of particle P at time 8. Well, we were given a velocity graph, and so if we look at time 8, this is time versus velocity. Right here is what we're looking at. Right there, the value is 1, right? And because given a graph of velocity, all we're trying to do is come up with the actual value. I'm not interested in the slope of that line. If we were thinking about the slope of this line, now we're talking about the derivative of the graph, which would be giving us acceleration. But since we're asking for velocity and we're given velocity, the y coordinate is 1, so v of 8 is 1. That tells me the velocity is positive, which means my particle is moving to the right. And in this case, since we're starting to the left of the origin and moving right, particle P is moving toward the origin. So particle P, we can say, is moving toward the origin. And then we already discovered that particle Q is moving away from the origin. So particle P is moving toward the origin. And we're going to say at t equals 8, because that won't always be true. This is just for the time that we computed right now. And then particle Q is moving away from the origin. I'm running out of space here, so I'm going to go ahead and try to abbreviate a little bit. Moving away from the origin at time t equals 8. So this is going to be a really good introduction to what we're going to be talking about here for the rest of the lesson, because we're going to take a lot of these ideas of particle motion that you've covered. Now, you may have understood or heard people talking about things that are covered or not covered on this year's exam. We know that for this specific exam, for AB, for students that are in Calc AB, the particle motion topics will be included on the exam through derivatives. So taking derivatives, the things that we were doing here, except for the position part, that will be on the AB exam. But for Calc BC, all of the particle motion from Unit 8 and earlier, including integration along the x-axis or the y-axis, everything that we did on here will be on this year's exam. So this will be really good experience and practice for what you're going to see this year. So let's take a little quick overview of what we're going to be doing here for the next 25 minutes as we finish this lesson. So every time that Tony and I give a lesson, you're going to see a little diagram like this, and it's going to share a couple of things. Number one, it's going to tell you what we're doing today. After we follow up from the warm-up, what you should already know, meaning these are the things that we need to know in order to do this lesson. They could be things from earlier this year, or they could be things from previous courses. Typically, on those what you should know part, those are the things that Tony and I are going to continue to kind of embed and review as well. So that way, if you're not completely familiar with them, you're getting kind of a built-in AP prep review during the lessons as well. And then what you'll be able to do, meaning this is what we're going to focus on in this lesson. So at the end of the lesson, this is a sample kind of problem that you should be able to understand and solve if you're following along and doing the problems with us. So today we're looking at topic 9.1, which in the AP's curriculum is called Defining and Differentiating Parametric Equations. So this is one of those topics that for this year only is not going to be on the AP exam. But again, like I mentioned before, even though it's not going to be tested, all the things that you're going to do in it are tested. And so just like the warm-up, it's a really good chance to review those previous topics, as well as see an important topic that when you go on to the next course or you go into college, your future professors will have expected you to have seen and learned. So what should you know? Well, we should know how to differentiate a function, taking derivatives. We should know how to connect position, velocity, and acceleration by taking different derivatives. And we should know how to find the slope of a tangent line, as well as write an equation of a tangent line. So how are our questions today going to look different than what we did on the warm-up and what you did earlier in the year? Well, here's a little example that I wrote up that it says the particle is moving along a curve at time t and has position x of t, y of t. A graph of x of t is given below, and we also know the equation for y of t to be sine of t. Find the slope of the line tangent to the path of the curve at t equals 1. So really the big idea question today is going to be, how can we find the slope of a line tangent to a curve in parametric form? So we're going to start building on that. And as we build on that, like I said, we're going to be reviewing a lot of previous content. So let's go ahead and jump into it. All the problems that we see on here, just so you know, at least for today and most lessons, are going to be new and unique problems that you haven't seen before. So I'm going to make sure that we create good problems that are not just rich and rigorous in content, but also are the kind of problems that you might come to see on a normal AP exam. Tony and I have nothing to do with the writing of the AP exam. We have no insights on the AP exam in terms of what it's going to look like, but we do have a lot of teaching experience, and we've seen a lot of problems, and we've written a lot of problems for our own students. And so we want to give you opportunity to engage problems in different, unique ways to fully prepare you for the AP exam. So let's take a look at this. So parametric motion allows us to extend our understanding of particle motion along an axis. So in the warm-up, particle P was moving just along the x-axis, and particle Q was moving just along the y-axis. And that's what we learn about in Calc AB, is just one particle moving back and forth along an axis. Parametric motion allows us to extend those ideas, extend those concepts into a plane, or we would call rectilinear motion. So now it's not bounded by just moving along an axis. It can move sort of freely in an XY coordinate plane. So in order to do this, we're going to have to involve 3 variables instead of 2. And the third variable, we're going to call that a parameter, which typically, at least in this lesson, is going to be time. T is our parameter. So think about the following scenario. This might kind of give you an idea of how these parametrics work. And hopefully in your pre-calculus classes, you have some exposure to parametric equations to kind of see how they work. If you haven't seen parametrics or you didn't learn those in pre-calculus, it's not a big deal, because very fortunately for us, parametrics are really intuitive, because how you really think about things in real world time anyway. So imagine a ball is kicked from the ground at a 30-degree angle. And I've got a little picture here. The scale is different, then it's not counting by the same scale. That's why it doesn't look like a 30-degree angle. But it's a 30-degree angle with an initial velocity of 20 meters per second. The ball travels along a roughly parabolic path that's modeled by the equation and the graph below. And you'll notice that we're using a gravitational constant of -10 meters per second squared. That might bother some of us because it's not as precise, but if you're in AP Physics 1, you're probably familiar of using that rounded number for the calculations because it's still decently accurate and it lets the calculations become much simpler. So this equation, based on this information, you're not going to have to know how to come up with the equation, but the equation is going to be y equals -x squared over 60 plus x over the square root of 3. That would be the equation that models this situation using our kinematic equations from physics. So the equation above is great because it tells us, where the ball is located, right? If I know the x coordinate, I know the y coordinate. If I know how far the ball has traveled horizontally, then I can tell you how high the ball is. Or if I know how high it is, I can tell you the 2 times or the 2 locations where it's that height. Unfortunately, this equation does not tell us when the ball is at each location, which is pretty important. So using parameters, we could convert this equation. And the AP exam does make you convert equations like this from rectangular to parametric form. So we're not going to worry about that right now. It's a pre-calculus type concept, but if you're interested, there's some really good Khan Academy videos that will show you how to convert from parametric form to what we would call rectangular form and vice versa. But in this situation, the parameters would be x of t is 10t radical 3, and y of t is -5t squared plus 10t. So this 2 equations that we're given now tells us I can figure out the x location, how far the bar's traveled horizontally, based only on time, and I can figure out how high the ball is based only on time. So if I knew it's been in the air for 1 second, I could tell you how high it was. I don't have to know the x coordinate to do that. Whereas in the rectangular coordinate, we would have to know the x values to compute the y values. So there's a lot of advantages to doing things in parametric form. So let's look a little bit more closely at this problem. These are the same 2 equations that I had for that problem, but the only difference is now I've kind of gotten rid of the graph, but the x value, the x position is given by that same equation, and the y position is also there. And it says the functions above really allow us, I'm going to put this in quotes, to separate the motion equations into x and y components. We can really think about the x location and the y location, the x position and the y position separately, but also we can analyze or group them back together depending on the situation and what we want to know. Because if we know that if we kick a ball in the air in a kind of a parabolic path, it's really doing 2 things. It's moving horizontally, and you can imagine how that would look by looking at the shadow that it casts on the ground, right? Looking at the shadow of the ball, the shadow is only moving horizontally on the x-axis, but it's also moving vertically up and down. And so we can separate those 2 equations and realize that these things are doing kind of 2 separate ideas, but grouped together, it gives us a full picture of the whole motion of the ball. So using example 1, let's consider the equation above. Let's describe the motion of the ball. And I say describe the motion, I'm going to actually add a little word there. And it's going to be, let's describe the direction of motion. That's what I mean by describing the motion. Let's describe the direction of motion of the ball, meaning which way is it moving? Well, we knew that when we were learning earlier topics, the velocity would tell us that, right? If I want to know the direction something's moving, find the velocity. If it's moving along the x-axis, the velocity will tell us whether it's moving left or right. And if it's moving along the y-axis, the velocity will tell us whether it's moving up or down. Well, since we're doing parametrics, it's kind of doing both. So we're going to look at these 2 things disjointly. So if I want to figure out the direction of motion, in the x direction, let's start with that way first. I really had to figure out the velocity in the x direction. And the velocity is going to be the derivative of the position, right? So I have to take x's derivative. And notice we have 10t radical 3. So here's a little bit of a good derivative practice. I've always found that with my own students, sometimes the simplest derivatives are the ones that cause the most confusion because they overthink them. This question looks a little bit different, and students sometimes try to do the product rule or some kind of square root ideas. But remember, we could rewrite this really as 10 radical 3 times t. What the same thing is, we typically put the t in front of the radical. That way there's no confusion of whether the t is underneath the radical or not. So this is more of a way to clarify what we're trying to say. But 10 radical 3 is just a constant. It's just a single number. So a number times t, when I'm taking the derivative, is just going to be the constant, right? So we know that the derivative of 10 radical 3 times t is just 10 radical 3. So the velocity in the x direction is 10 radical 3. And then doing the same thing for the y, if I want to find the velocity in the y direction, we're going to go ahead and differentiate the position of y, and we're going to get negative 10t plus 10. And we want to find specifically the direction of motion at the time t equals 1.5, right? So I got to plug in 1.5 for t for both of these. Well, for x, there's no reason to, because the velocity is just 10 radical 3. No matter what's happening, it doesn't change. So our velocity in the x direction at time 1.5 is just going to be 10 radical 3. And we know that's a positive number, right? So that's that in the x direction, at least, the particle's moving toward the right. Now in the y direction, if we figure out the velocity at time 1.5, we can plug 1.5 into here, and we get negative 10 times 1.5 plus 10. That gives me negative 5, if I simplify that, which is less than 0. So in the y direction, which is up and down, the velocity is negative, which means it's moving down. So the overall direction is going to be this particle at t equals 1.5. This particle, or this ball in this situation, is moving down because of the y and to the right. So the motion is going to be down and to the right. Now I want to jump back to that previous slide where we could see the picture of this, because this slide right here, this is the x and y rectangular coordinates. You can't see time in this picture here because it was the x and y equation. However, we just said that we knew that at time 1.5, the ball is moving down and toward the right. Well, if you imagine this ball, right, moving along this path like this, well, if it's moving down and toward the right, we know that at time 1.5, we're somewhere in this vicinity right here. This is the location where the ball is moving down. And of course, because of the problem that this ball is always moving toward the right. But somewhere in here is where we would have t equals 1.5. So let's try a couple more to see if we can get our minds around these concepts, right? Where we're connecting things that you've known from earlier in the course with some new ideas with parametrics. I hope you're realizing that in parametric motion, everything is the same. The concepts are the same. The idea of position, velocity, acceleration, total distance, all those things are the same, except for now we have components that we can act on individually to give us a better picture. So one of the things that I mentioned earlier is that the exam is going to not just test you on concepts, they're going to test you on skills, and they're going to test you on mathematical practices. And so one of those skills that you'll see embedded in questions is that you understand these ideas through different representations, meaning sometimes students know how to work with equations. If I give you an equation, you can take a derivative, you can set it equal to 0, you can solve it, you can get an answer. But to have really good conceptual understanding of what's happening in calculus, you have to also connect that to what do those same ideas look like through a table? What do those same ideas look like if I'm only given a graph? How do those ideas look if I'm given an equation or a graph of x of t, or x prime of t, or x double prime of t? So there's all kinds of connections that you're making depending on that beginning information. If you've ever looked at previous AP exams or exam problems, you'll notice you get a very good selection, a variety of what stimulus or what kind of prompt they give you. They give you some graphs, some tables, some equations. Sometimes you're given f or f prime or f double prime, and putting all those things together is really going to be indicative of a student that has mastered the material beyond just computation. So example 2 is a good example. We can look at that because now we have a graph. And not only do we have a graph, but the graphs of f prime, right? Remember, we have position, which is x, and then x prime, which would be considered the velocity, right, of x. I should probably not primes there for velocity. The position is just going to be the velocity in the x direction. And then x double prime is going to be the velocity's derivative, which happens to be the acceleration, right? Those same connections we made before in AB type topics are going to be still included here. And so now we're given a velocity graph of x, and we have this idea that we have the position of a particle moving is given by x, y. So instead of just simply calling it a coordinate x comma y like we do in rectangular coordinates, it's x of t and y of t, because the t value is going to be what helps us to understand what those individual points are. And we're given an equation for y of t, and the graph of x of t is above, and it consists of 3 line segments. So we want to find the acceleration vector. So obviously that word vector might be new to you if you haven't done parametrics before in pre-calculus or even this year. When we write our coordinates, x comma y, that's just an ordered pair. But when you're doing things in parametrics or other coordinate form, we can call those coordinates vectors because they're dependent upon time, and they're not just a single scalar product. They have a magnitude and a direction. So it's not going to change any of the math we do. It's just sort of the underlying ideas behind it that allow us to do to extend the things that we've learned in Calc AB to Calc BC. So we want to find the acceleration vector at time t equals 3. Well, to do that, we should first find the acceleration. So let's start with the x acceleration. So we know that the acceleration in the x direction at time 3, well, based on what we wrote up here, we know that's going to be the derivative of x's velocity at time 3. Well, luckily for us, we're given a graph of x prime. And remember, we already mentioned that x prime is the velocity. So if I want to figure out what acceleration is at 3, I have to look at the derivative of velocity at 3, which is the slope of this graph. That's the connection that we have to make for the AP exam, is that when you're taking a derivative with a graph, we're thinking about the slope of the graph at that point. And so at t equals 3, this is our time, and this is going to be our velocity. At time 3, we're right here on the graph, and I'm not interested in the velocity itself. I'm interested in the acceleration, which is the derivative of this graph, right? So the slope of this graph, luckily for us, this point is part of a linear segment. And so the derivative is going to be the slope of that line from endpoint to endpoint. You don't have to try to figure out the slope right at this point. Sometimes my students earlier in the year, when we would have a derivative of a graph where it's kind of in the middle of a segment, they were trying to figure out the slope right there by connecting from that point. But this is part of a linear function. And so the slope of the derivative never changes no matter where you are. And the average rate of change in this case is always equal to the instantaneous rate of change, meaning if I pick any 2 points on this line segment and find the slope between those 2 points, that will be the derivative of every point on the graph. And so in this case, the slope of this line, we can clearly see this going down 3 and over 2. So we get a negative 3/2 slope. So our acceleration at time 3 in the x direction is negative 3/2. And now we also have the same thing in the y direction. The difference here is we're not given a graph of y. We're given an equation for y. And this is not y prime, it's just y of t. So if we're going to find the acceleration, we're going to have to move down this sort of ladder 2 derivatives, right? To go from position to acceleration, we need to take 2 derivatives. So let's start by finding y prime. That would be the velocity in terms of y. And so we have a derivative of an exponential function. And you remember the derivative rules for exponentials means e to the u, right? If I'm taking a derivative, will stay the same, but then we have to multiply by chain rule by the derivative of the exponent. So in this case, 2e to the 3t, the derivative is going to stay 2e to the 3t, but by chain rule, I have to multiply by the derivative of 3t, which is just 3, which gives me, if I simplify this, a velocity of 6e to the 3t. And I don't want the velocity. We're trying to find acceleration. So keeping your work organized is going to be really helpful. And so the acceleration in the y direction is going to be the velocity's derivative now. And same rule applies. we're going to have 6e to the 3t times 3 again using chain rule, or simplify that to 18. Oops, I think I lost my my slide there for a moment. It didn't seem to like that. I think somehow it deleted my slide. That was fun there. Here we go. 18e to the 3t. One of the exciting things about doing these live sessions is there's no no planning for the unexpected. So if something goes wrong, you get to watch it live, and we can't plan for it and we can't edit it out later. So hopefully that won't happen very much this week. So here's my acceleration vector, and at time 3, acceleration at time 3 just plugs 3 into our equation, and we're going to get 18e to the 9th power, which means our acceleration vector, the x component was -3/2, and the y component was going to be 18e to the 9th power, like that. It looks like we're using parentheses. Sometimes it looks like you're calling that an ordered pair. With vectors, we can use parentheses notation, and sometimes you'll even see that with these like sort of pointy brackets. And these pointy brackets are pretty common because the pointy brackets are a good way for us to clarify that we're dealing with parametrics and vectors and not dealing with ordered pairs. So typically we can use parentheses as long as we understand the context and there's no ambiguity of what you're trying to discuss. But you might also see or use those kind of pointy brackets to be more clear that we're talking about parametrics and vectors. So I'm going to skip example 3 for right now so we can get through a couple more problems that might help you as you move on and get ready to do the AP practice. But on that link underneath the video of resources, there's a nice document that you can download or print off, and it has all these problems and all the notes there, and that probably be in there. And then in the next day, you should have the typed up solutions to all these. So if you want to go back and try example 3, you can, and you'll see the solutions in there to see if you did it correctly. The last thing I want to mention today, which is kind of a big important idea of topic 9.1, is this idea of a derivative, right? And that we know we're interested in finding things like dy dx, right? The derivative of y with respect to x. And so we have these parametric equations, but in general, even though we're doing parametric equations, we're involving time. When we put them together, the graphs that we're graphing are still going to be in an xy plane. And so because they're in an xy plane, you know, we're always interested in this idea of a tangent line, right? And we know that the tangent line of any graph in the xy plane has a slope of dy over dx, right? dy over dx is going to give us the slope of that tangent line. That doesn't change just because we're in parametrics or polars. The second half of Unit 9 is going to involve polar equations and polar graphs and extending those ideas that you learned earlier in the year to polar functions. And even with polar functions, we'll discuss this idea of tangent lines to a curve. The tangent line to a curve, whether you're in rectangular coordinates or whether you're in parametrics like today, or whether you're in polar coordinates, the tangent line will always have a slope of dy over dx. So we have to figure out how we can do that. And so we know that dy over dx is going to be equal to dy over dt over dx over dt. And that should make some logical sense, right? Because we know dy over dx, if we think about this as dy over dt over dx over dt, then we can multiply by the reciprocal of this and call that dx or dt over dx, and that will reduce to dy over dx, right? So we can see how dy over dt over dx over dt, the ratio of those two quantities would give us dy over dx, which will be the slope of the tangent line. So whenever you see the phrase find the slope of the line tangent, immediately you should realize a tangent line slope is always going to be dy over dx, and we got to figure out how we can compute that. Well, if we're in parametric form, we compute that by finding dy over dt and then finding dx over dt. So on this example right here, they were kind enough to just to go ahead and give us those values, right? dx dt is given by this, and dy dt is given by this. And to find the slope of the tangent line, which is dy over dx. We just have to figure out dy over dt over dx over dt at time equals 4. So if I plug in 4 into these equations, dy on top, that's going to give me at t equals 4, the natural log of 5 over, plug in 4 to the second equation, and you're going to get 4 squared minus 3, which is 13. So we know the slope of the tangent line for these parametric equations is going to be simply whatever the natural log of 5 over 13 is. So that idea is going to be a nice, pretty important topic. And if you think about some questions that we could ask with this, right? So I'm going to show you a quick problem here that we're not going to have a chance to do together. Again, I would encourage you to kind of try it. I want to kind of mention how you might tackle this problem here. So a particle moves along a curve in the XY plane such that its position, right? We're talking about parametrics, x of t and y of t, is given by the equations 1/3 t squared or t cubed minus 2, and then y of t is going to be 3t squared minus 4t plus 1. And the question is going to be find all the times where the line tangent to the path of the particle has a slope of 2. And so I want to at least begin to set this up for you, so that way when we get done here in the next minute or two, you'll have a chance to back and see if you can finish this problem out. But I want to show you how you might set this problem up to begin to solve it. Because again, look for the key words in the question. Sometimes we get so overwhelmed by the upfront information that we get overwhelmed by that and start focusing on this instead of really focusing on what they're asking, right? So the question is, we're talking about when the line tangent to the path of the particle. Well, we know that the line tangent, the slope of that is the same thing as saying dy over dx. So what they're asking is, when is dy dx equal to 2? And we also know that we have a way to find dy over dx, right? Dy over dx is going to be dy over dt over dx over dt. And so if we found dy over dt and dx over dt, we could just plug those in. And we're given an equation for y. So if I wanted to find dy over dt, that's just the derivative of y with respect to t. So in this case, this derivative becomes 6t minus 4. And then similarly, if I wanted to find dx dt, I'm taking the derivative of x with respect to t. And this derivative just becomes nice and clean as t squared. So to solve this problem, I know that dy over dx, which is supposed to equal 2, can also be found by taking dy dt over dx dt, which means the 6t minus 4 by dy dt over dx dt, which is t squared, should be equal to 2. And this is going to be the equation that we want to solve. If we can solve this algebraic equation, now we're going to be able to figure out what those t values are, find all the times t to do that. I'm going to put off here to the side. If you do solve this, the solutions would end up being 1 and 2. So maybe you can kind of go back and see if you can finish solving that one. How would you solve the algebra? I've always found that sometimes it's interesting because sometimes my students will do such a great job with the calculus, and then the algebra at the end is what trips them up. So it's always important not just to practice the calculus ideas and skills, but also those little algebra skills. That way you're not losing points because of the algebra misunderstanding. So at the end of the lesson, let's take a look and debrief and summarize a little bit. An enduring understanding is something that hopefully these little topics will build up and work together to help you have a better concept of how calculus works. And so here we're kind of get the understanding that derivatives can allow us to solve real world problems involving rates. And a couple of key takeaways that I hope that you'll remember moving forward is that the slope of a tangent line in parametric form is given by this equation. And then also the concepts of motion in 1D, that means moving along the x-axis or moving along the y-axis, just those basic motion problems. Those same exact concepts and ideas can be extended to 2 dimensions or parametric forms. A couple of common errors, and Tony and I will continue to have each lesson some things to kind of remember or look out for. These are actually errors or things that you should remember. If you don't, the mistake of these are what would cause the error. To always consider both components of a function, meaning that example we did said describe the motion of the particle. sometimes students only look at the X direction or the Y direction and say things like, it's moving to the right, or it's moving down, instead of realizing these are both together and the particle is moving down and to the right simultaneously. And then the slope of a tangent line is always dy over dx. Even if you're in parametrics, even if we're in polar form, the tangent line to a curve is the rise over the run, which is going to be the change in y over the change in x, which is dy over dx. And then also be really careful when you're solving problems. Sometimes they give you an equation or a graph or a table of x of t or y of t, and sometimes they give you x prime or y prime, which is the velocity. You really have to pay attention to which equation you're given and what to do with that equation. So at the end of every lesson, we're going to have an AP exam practice problem. You're not going to need to solve it right now, but what's going to happen is the warm up for tomorrow, the warm up for the next lesson will always start off with the same problem. So I'm going to put the problem on the board, and if you don't have the files, or you haven't downloaded them, or you can't download them, you don't have them printed out, maybe get your phone out and take a picture of the screen and see if you can find some time before the next video to try these problems. It's one stem with part A, B, and C that's going to really tie together the things that we talked about today, as well as a lot of those previous ideas and concepts that are embedded into today's lesson that will be on the exam come springtime. So take a little picture of this, and then tomorrow at 9 a.m. time, live, Tony Record will start with this problem, kind of walking you through it line by line and making sure that you were on the right track. But it really is going to be important as you begin your journey toward the AP exam to try these problems when you get a chance. So hopefully I'll give you another couple seconds to take a picture of this, and then we will look at the last slide here in a second. You'll notice on this problem, there's a lot of things going on. We have a graph of x of t. We have an equation of y of t, so we're connecting those representations, and a part of the graph of x of t is sort of this parabola shape here on the right, and in the stem, they give us an equation for that parabola. And we're going to be finding the velocity vector. We're going to be talking about the equation of the line tangent. We're going to see if you can extend the idea of how do you write a tangent line that doesn't change just because we are in parametric form. And then talking specifically about the horizontal movement. Is it moving left or right at time 7? So think about those problems. Think about how we've learned some things, what you understand about them, and how you might tackle these problems that maybe you have, but maybe you haven't seen before. This brings us to the very end of our very first lesson. Thank you guys for being our guinea pigs today. This was the first of 28 consecutive days of the week, Monday through Friday. We'll be doing these live lessons. Don't forget, these will be recorded and uploaded to the YouTube channel shortly after the videos are done, so you can come back and watch them later. And don't forget the full complete schedule that the College Board's released for 34, I believe. 30 or so of your AP exams are going to have these opportunities for you to join live or watch the recorded lessons with some different AP teachers around the country. So thank you so much for joining us today. Don't forget, we'll be on here tomorrow. I hope that you will join us again each and every day. Tomorrow morning, Tony Record will be giving the lesson, and then you will see us kind of bounce back and forth each day between the two lessons. So have a great day. Make this a great day. Get a little bit better every day as you prepare for the AP exam, and take care of yourself. We'll see you soon.